As exam number 3 approaches, let's take a moment to review some of our recent topics, including the rules for phasors, the transformer, that's the ideal transformer, and three-phase systems. We'll start with Ohm's law. For AC circuits, we describe a voltage as a current by an impedance, or you could describe that as a current is a voltage divided by an impedance, or an impedance is a voltage divided by a current. Power. Complex power is the voltage vector by the complex conjugate of the current. For both of these, we can use the cover-up method. For example, if you wanted to calculate complex power, that is a voltage times the complex conjugate of the current. So power complex is voltage by complex conjugate of the current. If you want to define the voltage, that is the complex power divided by the complex conjugate of the current. And if you wanted to find the complex conjugate of the current, that is a complex power divided by the voltage vector. If you do some substitution, you can put these together and say that complex power is a voltage by the complex conjugate of the current is equal to the magnitude of the current squared by the impedance is equal to the magnitude of the voltage squared divided by the complex conjugate of the impedance. Do be careful with the term magnitude. For example, if you had a current of 33 amps at a phase angle of negative 37 degrees, the magnitude is 37. Be sure you use the magnitude, which is the value in the polar form. It's the value of the scalar. We explored series circuits. We talked about a total impedance, which is the summation of the individual impedances. We explored impedances in parallel, where 1 over the total impedance is equal to 1 over the first impedance, plus 1 over the second impedance, and so on for as many impedances that you have in parallel. Eli the Iceman was mentioned. That was an easy way to remember that voltage leads in an inductive circuit. So this is inductive. Voltage comes before current. And over here, current leads in a capacitive circuit. So there's the capacitive part. You'll find current before the voltage. Closely related to that concept was the fact that vectors rotate in the complex plane. So if this is your voltage vector, and if this was your current vector, we would say that the voltage is leading the current because these phasors rotate in a counterclockwise direction. So you, as the stationary observer, would first observe the voltage vector, then sometime later you would observe the current. And that's right here. Voltage leads current in an inductive circuit. We've used the voltage and current divider many times at this point. The voltage of interest is equal to the impedance of interest over the total series impedance by the source voltage. We have to make a big caution here that this is the total series piece. The current divider. The current of interest is equal to the total parallel piece over the impedance of interest by the source. Once again, we have to make a big distinction here. This is the total parallel piece. It is not, definitively not, R total or Z total. For example, in this circuit, this is the total parallel piece that goes here as Z total. Do not make the mistake of using the total circuit impedance, because that has absolutely nothing to do with the current divider rule. Look at it this way. If there's a current here, there's going to be the same current here, which means this particular problem can be redrawn like so, where here is our original current, and these are original R2 and L2. Reactance and impedance. They're similar, but they are not the same. Inductive reactance is defined as 2 pi FL, or you'll occasionally see it as omega L, where omega is equal to 2 pi F. Capacitive reactance is equal to 1 over 2 pi FC, or occasionally as 1 over omega C. You'll notice there are no angles associated with reactance. Reactance is a scalar. Impedance, on the other hand, the impedance of an inductor is J by the reactance. So it takes whatever reactance it is and makes it point straight up on the complex plane. So if you had a pure inductive circuit, it would be at an angle of 90 degrees. The impedance of a capacitor is negative JXC, which means the impedance of a pure capacitive circuit would point straight down, so negative J. We visited the ideal transformer. We called this side the primary and this side the secondary. A transformer was a ratio machine, so the number of turns in the primary over the number of turns in the secondary, for example, 4 to 1, is equal to the voltage in the primary over the voltage in the secondary, is equal to the current in the secondary over the current in the primary. You'll notice it goes primary, primary, secondary. It's very easy to get those backwards. So what I do is I typically define a side as the high voltage side and the low voltage side. So here, because there's 4 there, it's 4 to 1. This is the high voltage side, this is the low voltage side. And I know that on the high voltage side, I'll have a high voltage but a low current. On the low voltage side, it's low voltage, high current. And of course, the other piece we need to know is that the complex power in the primary is equal to the complex power in the secondary. On a power flow diagram, it would look like this. Power in, power out. There would be no losses. For our next discussion, we'll actually talk about some of these losses. We'll talk about the I squared R losses, and we'll talk about the core losses that are associated with a non-ideal transformer. But for now, that's what you need to know for an ideal transformer. Our last topic was three-phase systems. A number by itself can generally be assumed to be RMS and a voltage line to line. Some examples: 208, 480, 4160. Voltage line to neutral is equal to voltage line to line over the square root of 3. For example, 120 volts is equal to 208 divided by root 3. Our last topic from our previous discussion were transforms, where you could take a delta system and conceptually convert it over into a y by dividing by 3. And that was true as long as the system was balanced. Here, balanced means that all of the voltages are equal across all 3 phases, and each load has an equal impedance. We used the term phase, and we have to be careful with that because it has two different meanings. If you are in a Y system, it means one thing, and if you're in a delta, it means something else. In a Y system, you might have something that looks like this. We would describe this piece here as a single phase. If we were to talk about the phase impedance or the phase voltage, we would be referring to just this piece here. In a delta, this would be considered a phase. With that definition, we can make a few related statements. The phase current is equal to the line current. That's an obvious statement, being as these are in series. So the line current, as measured here, would be the same as the phase current. The voltage line to line is equal to root 3 voltage phase. We've used this quite a bit already, except we didn't call it phase. We probably called it voltage line to neutral. You'll notice I did not use vectors in this case because we are purposely ignoring a 30-degree phase shift that's associated with this conversion. For the delta, the voltage line to line is equal to the phase voltage. So there is your line to line, and it happens that your phase is connected across line to line. Therefore, voltage line to line is the phase voltage. The line current is equal to root 3 by the phase current. Once again, we are not using vectors because we are ignoring the 30-degree phase shift. Here's an example that puts all these thoughts together. We'll assume this is balanced, that there are 2 ohms and 8 millihenries per phase. And we're looking to solve for these line currents. We'll assume 480 volts and 60 hertz. Your opening move is to calculate the reactance of the inductors. 2 pi by 60 by 0.008. 2 times pi times 60 times 0.008 gives us about 3 ohms. We'll call it 3.02 with 3 sig figs, which means the impedance of the inductor is J 3.02 for a total phase impedance of 2 in parallel with 3.02. That's 2 invert plus paren 3.02 J. Looks like I forgot the J there. Invert equals invert equals. So that's 1.39 plus J 0.92. There's at least 2 ways to solve this problem. The first method is to convert it into a Y single phase representation and then solve it. The second is to calculate the current through a single phase and then multiply that by root 3. So method 1 and method 2. The impedance of a Y is the impedance of the delta divided by 3. Our delta impedance is already queued in the calculator, so we just divide that by 3. So the impedance of the Y on a per phase basis is 0.463 plus J 0.307. Our line-to-line voltage is 277 at a phase angle of 0 degrees. We are ignoring the phase shift. This 277 volts is this voltage divided by the square root of 3. So we've taken a line to line and we've converted it to a line to neutral for our per phase solution. From there, the current can be calculated with Ohm's law. So 277 divided by 0.463 plus J 0.307. Being as current is already queued up, we're going to divide by 277, and then we'll invert the result, giving us a total current of about 500 amps at a phase angle of negative 34 degrees. Which means if you were to hang a current meter on the circuit, such as this one here, you would expect to read 500 amps. Pictorially, this is what we did in this method. We took 277 volts and then our per phase impedance, which was 0.463 and J 0.307, put those two together and then calculated this current. Method number 2 would have us solve for this current directly, knowing that there's 480 volts across a phase. So the current in a phase is equal to 480 volts divided by the impedance of that phase, which I believe is right here. So 1.39 plus J 0.92. So the current in a phase, and we got to be careful here. That means this current meter right here, that is the current in a phase. And this is a current in another phase. All right. So that's 480 divided by 1.39 plus 0.92J gives a current of 288 amps at a phase angle of negative 34 degrees. In our next step, we are going to ignore the 30 degrees phase shift, which isn't so strange because things like this little amp clamp, is not aware of phase shifts. So we can simply say that the current in a phase, and that's the current measured here using something like this, is 288 amps. The line current would be the phase current by the root 3. That's 288 times the square root of 3, and there is our 500 amps. For our purposes, I would recommend you stick with the delta to Y conversions, knowing that we're going to be doing a lot more of that type of operation in the future. Here's another example. I would like you to calculate the voltage on the load. We'll let the line impedance be 20 milliohms in series with a 160 microhenry inductor. We'll let the phase impedance be 2 in parallel with a J3 inductor. Your opening move would be to calculate the impedance, and I'll leave that up to you to show that this is J60 milliohms. Our next move is to convert this delta into a Y, but be careful. You'll notice that this is a parallel load. So what we want to do is calculate the phase as if it was the equivalent series circuit. So 1 over the impedance is equal to 1 over 2 plus 1 over J3. So the impedance per phase is equal to 2 inverse plus 3J inverse equals, that's 1.389 plus J 0.923. Conceptually, this is what we've done. We've taken this piece and we've said rather than represent it as a parallel, you can represent it as a resistance in series with an inductor. That resistance is 1.39 ohms, and that inductance is J 0.923. To convert this into a Y, remember that the impedance of a Y per phase is the impedance of a delta per phase divided by 3. So we're replacing this piece here with the equivalent Y. Notice we're not touching this piece, which means the line impedance remains unchanged at 20 milliohms and J 60 milliohms, but the load changes. And since it's already queued up in the calculator, we do a division by 3, and there it is. So that resistor is 0.461 ohms, and the inductor is J 0.308 ohms. From there, we can use the voltage divider to calculate the voltage that would have been measured across the Y. That voltage line to neutral is 0.461 plus J 0.308 over 0.481, so there and there, and then plus J 0.368, so there and there, all multiplied by 277, because that is the voltage of the generator line to neutral. We enter that in the calculator. It tells us the voltage line to neutral is 254 volts. We convert that back into our voltage line to line is root 3 by 254, which gives us 440 volts. So back to the original problem, if you were to put a voltmeter right here, it would read about 440 volts, with the understanding that we have 480 volts coming in. As a recap, we were given a delta circuit and asked to calculate the voltage line to line as measured at the load. Our opening move was to convert everything into impedances. This particular problem was a bit tricky because you had a parallel component, and it works easier if you convert that into the equivalent series, which was done right here. From there, we did a delta to a Y conversion and sketched out our equivalent per phase circuit. And from there, we used the tools that we've used all along. The voltage divider gave us a voltage line to line, and then we multiplied that by root 3 to get back to the voltage line to line. So delta to Y, Y back to delta. Moving on to complex power. Suppose you're given 3 loads. Load number 1 is defined as 10 plus J 12 kVA. Load number 2 is defined as 15 kVA with a power factor of 70%, but it's inductive. Load number 3 is defined as 10 kW with a power factor of 80%, this time capacitive. As you start this type of problem, I would highly recommend that you draw the power triangle for each load. Load number 1 is very easy because it's given to you already. So that's 10 kW with 12 kVAR. Load number 2, you know it's inductive, so that power triangle is going to be upright. You're given 15 kVA and a power factor of 70. From your notes, you know that power factor is defined as cosine of theta, which is also equal to the ratio of real power to apparent power. It means that 0.7 is equal to cosine of theta is equal to the real power over 15k. Solving for theta, take the arc cosine of 0.7. So that's an angle of 45.6 degrees. And the real power will be equal to 0.7 times 15, which gives us 10.5 kW. And using Pythagorean theorem, you'll find that this is 10.7 kVAR. The third load is capacitive. It will have a power triangle that points down. We're told that it's 10 kW, and we'll use these same ideas to find the angles. I'll leave that up to you, but that works out to be 36.9. This here is 12.5 kVA, and it's 7.5 kVAR. The total complex power is equal to 10 plus 10.5 plus 10 plus J12 plus J10.7 minus 7.5 kVAR. I suppose we could have written this as minus 7.5. Would have been more appropriate. If you put all that together, the total complex power is equal to 30.5 plus 15.2 kVA, giving us a large power triangle, the summation of all three, as 30.5 kW and 15.2 kVAR. At an angle of arctangent 15.2 divided by 30.5, 26.5 degrees. Since we're here, we may as well calculate the line current. We have to add one more piece of information, and that is that this is a 480 volt system. To calculate that line current, we need to take this power triangle, which represents all three loads in all three phases, and we need to write it as a per phase equivalent. So you could think of the power triangle as being broken into three smaller triangles, where each triangle represents the per phase power. So that becomes 10.2 kW and 5.07 kVAR. Schematically, it looks like this. Where this is 277 volts line to neutral. We know that complex power is a voltage by the complex conjugate of the current. Therefore, the complex conjugate of the current is 10.2 plus J5.07 kVA divided by 277 gives us a line current of 10.2 plus 5.07 J by 1000 divided by 277. That's 41 at a phase angle of 26.4 for a complete current of 41 amps at a phase angle of negative 26 degrees. If you were to put your amp clamp right there, right, this thing would read 41 amps. Let's go back a little bit further and answer some voltage divider questions. For this problem, you're asked to find the voltage across the 4 ohm resistor, given that this is 120 volts at a phase angle of 0 degrees. This problem is relatively straightforward except for this piece here. As our opening move, we're going to want to convert that to a series impedance. So that's 3.29 plus J 4.70. So anywhere you see this in your calculation, replace it with this and you'll be in good shape. Using the voltage divider, the voltage on R2, this is R1, L1, R2, L2, R3. So the voltage on R2 is 4 over 2 plus J1 plus 4 plus 3.29 plus J 4.7, all multiplied by 120. And if you run that through your calculator, I think you'll find it's 44 volts at a phase angle of negative 32 degrees. Here's a current divider problem. Again, we'll let that be 120 volts, 2 ohms, J10, 8 ohms, negative J30. There are 2 ways you could solve this problem. The first way is to do a Thevenin to Norton, where you say this current is now 60 amps at a phase angle of 0 degrees. That 2 ohm resistor drops to that position. J10, 8, and I believe it was negative J30. And now you can use the current divider. First step is calculate the total impedance, which is 2 in parallel with J10, in parallel with 8, in parallel with negative J30. Gives you a total impedance of 1.58 plus J 0.169. Now the current on R2, I should have specified that. That's what we're curious about. We want to know the current through R2. The current through R2 is equal to 1.58 plus J 0.169 over 8, all multiplied by 60. So divided by 8, multiply by 60. And the current through R2 is approximately 12 amps at a phase angle of 6.1 degrees. So that was one way to solve the problem, was to take and recognize that this here was a Thevenin circuit, convert it into Norton, and then use the current divider. An alternative solution would be to calculate the total impedance as 2 plus J10 in parallel with 8 in parallel with negative J30, which gives you 8.23 plus J 3.32 ohms. From there, the total current is 120 divided by the total impedance, which gives you a total current of 13.5 amps at a phase angle of negative 22 degrees. From there, you can use the current divider. Be careful. When you use the current divider, you have to use this piece here. Do not use this piece. If you do, the answer will be wrong. So that's this piece here. Do not use it in the current divider. I think I've mentioned that before. I called it a trap. So the impedance total of the parallel piece is J10 in parallel with 8 in parallel with negative J30. So Z total of the parallel is equal to 6.23 plus J 3.32. And now we can calculate current through R2 as 6.23 plus J 3.32 over 8 by this current. And if you run that through your calculator, I believe you'll find the current is the same 12 amps we calculated earlier at an angle of 6.1 degrees. One more example and we'll call it a day. In this problem, we're given an ideal 4-to-1 transformer, a 20 kW load with the power factor inductive, and a necessary voltage of 120 volts. We're asked to find the source voltage and the source current. For this type of problem, work the problem right to left, stopping at each point along the way. We start here. The voltage on the secondary of T1, assume that's T1, is equal to 120 volts. That's a given. Next, we need to determine the current from the given power factor and voltage. So this here is 20 kW, and as far as the angle is concerned, that's inverse cosine of 0.77. So that's 39.6 degrees. The power factor is also the ratio of real power to apparent power. So 0.77 is equal to 20 kW over S. So the apparent power is 20 divided by 0.77. So that's 25. You may as well call that 26. The complex conjugate of our current will be complex power divided by voltage. So complex conjugate of current is 26 kVA at an angle of 39.6 over 120. 26 at a phase angle of 36.9 equals by 1000 equals divided by 120 equals. That yields a current of 217 amps at a phase angle of, be careful, because here in the calculator we have the complex conjugate, so we need to convert that over to the paper as negative 39.6 degrees. So current is 217 amps at a phase angle of negative 39.6. Next, we reflect those values through the transformer. So the voltage on the primary of T1 is 120 times 4. And the current on the primary of T1 is this current divided by 4. That brings us to the source. And we have to use Kirchhoff's voltage law to describe the summation of all the voltages in this loop. The source voltage is equal to 480, that's here, plus the voltage here, which can be described as a current times the impedance. So here's the current, and here's the impedance. Which finally gives us a source of 485 volts at a phase angle of negative 0.51 degrees. There's the voltage, and there is the current. There is an easier way to work this problem. Recall that the complex power in the primary is equal to complex power in the secondary, which means we can conceptually take this entire power and push it across the transformer, which would eliminate a few steps for us. It goes something like this. These pieces remain unchanged. Our 26 kVA at a phase angle of 39.6 degrees comes across, and our voltage comes across as 480 volts. Once you've gotten that far, complex power is the voltage by the complex conjugate of the current. Solving for complex conjugate of the current, solving for the current. Taking a trip around the circuit using KVL, you can make a statement about the source voltage, and that brings you to the completion of the problem, where you find that the source will be 485 volts at a phase angle of negative 0.51 degrees.